Hello, my name is Jan Kudlika and I'm from Uppsala University in Sweden. My talk on probabilistic programming for birthdate models of evolution using an alive particle filter with delayed sampling is based on the paper of the same name, which I wrote together with Lawrence Murray from Uber, Fredrik Gronqvist from Swedish Museum of Natural History, and Thomas Schön from Uppsala University, and which was previously presented last year at UAI. Let's first refresh some basic concepts from biology. There are two types of processes that play an important role in the evolution of species. Speciation, when the population of a species splits and eventually forms two new species. And extinction, when all individuals of a species die out. Species with individuals alive at the present time are called extant species. In phylogenetics, before present time is used, which specifies how long ago an event occurred. Birth-death models of evolution model speciation and extinction processes as events. Waiting time between these events are exponentially distributed. An evolutionary process starts at some given time in the past with a single species. The result of this process is a binary tree, which we will call a phylogenetic tree or a phylogeny. Constant rate birth-death model, or CRBD for short, is the simplest model. Both the speciation rate, denoted by lambda, and the extinction rate, denoted by mu, are constant both over time and for all species. Different models admit changes to the speciation and extinction rates, both continuous changes and sudden jumps. To implement the CRBD model in a programming language is quite straightforward. Consider the CRBD function shown here. It accepts the time when the process starts, the speciation rate, and the extinction rate. We first sample a waiting time delta until the next event from an exponential distribution with rate lambda plus mu. If the waiting time is larger than t, the species has survived to the present time and we return a node of type extant. The argument t represents the length of the branch between this node and its parent. If the waiting time is smaller than t, we need to decide if this event is a speciation or an extinction by making a draw from a Bernoulli distribution with probability lambda over lambda plus mu. If S is true, we return a node of type speciation with the branch length delta and the left and right subtrees, which are obtained by calling the CRBD function twice, this time starting at time t minus delta. If S is false, we return a node of type extinction with the branch length delta. The result of running any generative birth-death model forward is a tree like the one shown here. This tree includes extinct species and is therefore called complete. A tree that shows the evolution of only the extant species and their ancestors is called observed. The observed tree, which corresponds to our complete tree, is shown on the right side. Looking back at the complete tree, we will distinguish between observed and unobserved or hidden speciation events. If both children of an internal node are ancestor of extant species, or simplified, both survive to the present time, we will call the speciation event observed. Otherwise, we will call it unobserved. Our goal is parameter inference. Given a model, a prior distribution of the model parameters, and an observed tree, which is reconstructed from our knowledge about the extant species, for example genomic data, we are interested in the posterior distribution and the marginal likelihood. We'll assume that the observation t is given without any error. As we have seen, writing generative models simulating phylogenetic trees as programs is very easy. For simple models, we are talking about 10 to 20 lines of code. Inference today is difficult and time-consuming, and it requires collaboration with experts from several domains that can find bespoke inference algorithms and implement them in existing or new software packages. Our solution? Probabilistic programming, of course. A naive approach would be to implement a generative model as a program, prune back the extinct subtrees from generated phylogenies, and reject those where the pruned tree is not equal to the observation. Obviously, no pruned tree will ever be equal to the observation, so this approach will always result in rejection. So let's do something else. We start with the observed tree and augment it with events that were pruned back. Along each branch of the observation, we'll use the generative models to simulate changes to the speciation and extinction rates, changes to the state in models with state, and hidden speciation events. For each hidden speciation event, we'll also use the generative model to simulate the hidden subtrees, starting at the time of the hidden speciation. Let's now return to the CRVD model. We traverse through all nodes of the observed tree except the root in the depth first order. For each node R, we look at the branch from the node to its parent. Let delta R denote the length of this branch. We sample the number of hidden speciations along this branch from a Poisson distribution with rate lambda times delta R. For each hidden speciation, we sample its time from a uniform distribution between the time of R and the time of its parent. In other words, we sample the times of events from a Poisson point process with rate lambda. We then call the service function, which is shown on the right side, to use the generative model to simulate the hidden subtrees. But this time, we are only interested to know if the hidden species or any of its descendants survive to the present time. If so, we have obtained a complete tree, which is not compatible with our observation, and therefore set the probability of execution to 0. And at this point, we can stop the execution. If no species has survived to the present time, we double the execution probability, since the hidden subtree might be both a left or right subtree of the hidden speciation event. When done with hidden observation events, we observe that there were no extinction events along the branch. And if R is a speciation, we also observe that starting at time of the node R, a speciation event occurred after 0 waiting time. Alright, we are now ready to run the probabilistic program using SMC. Let us recall how the bootstrap particle filter, the simplest of the SMC methods, work. After initializing the particles, we repeat the following procedure for each of the t time steps and for each of the n particles. We choose an ancestry index from a categorical distribution with the probabilities proportional to the weights at the previous time step. We then propagate the corresponding particle, and we calculate the new weight. If we are interested in the estimate of the marginal likelihood, we use the formula shown on the right side. Recall the program for the CRVD model and the service function. If during simulating the hidden subtrees any species survive to the present time, we set the particle weight to 0. In extreme cases, all particles might have 0 weight, and the filter degenerates. In 2015, Del Moral et al. Considered a similar problem in setting with indicator potentials. That is, where the weights are either 0 or 1. They presented an alive particle filter, which repeated the resampling and propagation step for particles with 0 weights. We have extended this method to work with importance weights. This method requires only a few modifications in the bootstrap particle filter. First, we'll repeat the resampling, propagation, and weighting steps for each particle until its weight is positive. We'll also count how many propagations we did, including the rejected ones. To be able to estimate the marginal likelihood without bias, we need to repeat the whole procedure for one additional particle. Note that neither this particle nor its weight will ever be used for anything. Resampling at the next time step will only use the first n particles and their weights. Also, calculating the estimator of the marginal likelihood, shown on the right side, will only use the weight of the first n particles. The only reason why we are doing this is to include the number of propagations in PT. We have also used delayed sampling in our work. For those of you who are not familiar with it, consider the following example. Let nu be a gamma distributed random variable with shape k and scale theta. If we need to sample a number of events, denoted by n, from a Poisson distribution with rate nu times delta, we can exploit the conjugacy relationship between the gamma and the Poisson distributions, and sample n from a negative binomial distribution with the given parameters. Based on the sampled value, we then update the distribution related to nu. The same approach can be used for sampling from an exponential distribution as shown in the right column. Exploiting the conjugacies can be automated by an algorithm known as delayed sampling. We have implemented the conjugacies shown on the previous slide in Burge, a probabilistic programming language we used in our work. An interesting fact is that using this approach, there is actually no need to sample the speciation and extinction rates at all. The posterior distribution for both rates can be expressed as a mixture of gamma distributions corresponding to each particle at the end of their execution. In our experiments, we use the reconstructed phylogeny of cetaceans, which include whales, dolphins, and porpoises. This phylogeny, shown on the right side, has 87 extant species. We then compared the different inference methods, combining using the bootstrap particle filter and the extended alive particle filter with immediate and delayed sampling. This graph shows a box plot for the logarithm of the estimates of the normalization constant, obtained by running the CRBD program multiple times, with different number of particles and different methods. We also implemented another model, which is called BISSE, Binary State Speciation and Extinction. This model introduces a binary state for species. Each state is associated with their own speciation and extinction rates. The state of a species can change at random times that follow a Poisson process. And finally, the state of the extant species is usually observed. In our experiments, the state represented the body length. The state 0 means small cetaceans whose body length was more than the median body length of all cetaceans, and 1 otherwise. The difference between our method and the standard SMC is even larger for the BISSE model. Our method yields an increase of the effective sample size and the conditional acceptance rate by a factor of 30 in comparison with standard SMC. We showed how phylogenetic birth test models can be implemented in PPLs, and showed the strength of the extended alive particle filter with delayed sampling for these models compared to the standard bootstrap particle filter. The extended alive particle filter is a general inference method that shows its strength in situations where particles are often assigned 0 weight. In the case where the weights are always positive, the extra cost of using the extended alive particle filter is negligible, making our method a suitable drop-in replacement for the bootstrap particle filter. Do you want to know more? Come and talk to us during the poster session later today. Thank you for your attention.